I'm Armen Kteyan from Siemens EDA. I am presenting a novel methodology of EM assessment in on-chip power grid and the methodology validation by measurements on real silicon. This work was performed in collaboration with University of Toronto, University of Minnesota, and CA-LETI. This is outline of the presentation. I'll demonstrate new approach to EM assessment based on airdrop analysis. We'll present modeling of EM stress evolution in interconnect trees and voiding models. Experimental validation of temperature-aware EM model with grid-like test structures will be demonstrated, and then validation of EM assessment flow with real silicon power ground grid degradation data will be presented. Finally, some conclusions will be made. Power nets in ICs supply voltages to the operational cells, therefore they carry unidirectional currents and are prone to EM failure. For this reason, checking EM rules for these nets is mandatory. The traditional approach to EM assessment in power grid is based on application of results obtained for single-link structures. It means that the interconnect layout is decomposed into individual segments, and for each segment, mean time to failure is calculated using Black's model. With this approach, the expected lifetime of overall system is determined from the failure probability of the first voided segment. But currently there is an understanding that application of this traditional approach is not correct, and particularly it results in the grid over-design. The first fact which is missed with the traditional approach but is considered with our proposed methodology is that power grid contains many redundant paths of voltage delivery to the functional blocks. Electric current is redistributed when EM voiding in one line causes a local resistance increase. Grid fails when voltage variation caused by increase of resistances exceeds a designer-specified threshold in any critical node. Therefore, the proposed methodology is based on analysis of EM-induced airdrop evolution in the interconnect. The second fact, which is missed with the traditional approach, is that the net in each metal layer consists of so-called interconnect trees. This is connected metal segments. Since metal atoms can diffuse from one branch of a tree to another, the decomposition of the tree is not allowable. The presented methodology is based on Korhone's equation, which describes EM-induced stress evolution in each branch. Atomic flux continuity in each junction leaves these stress equations in all branches. From this set of differential equations, we can find the locations where stress exceeds a critical value required for void nucleation. Note that Korhone's equation explicitly contains dependency on temperature-dependent diffusivity. Therefore, the analysis should be linked to thermal simulations for detecting temperature in each branch of the tree. With this 1D approximation, we use compact models to describe voiding-induced resistance increase of wires, downstream vias, and upstream vias, which allow further simulation of voltage evolution in the grid nodes. The initial voltages are calculated with matrix equation for voltages involving conductance matrix of the wall circuit and constant currents. So the conductance change is calculated based on voided resistors resistance change, and the obtained change of conductance matrix is used for recalculation of voltages. Summarizing, the following EM assessment flow for power grid is developed. The inputs for the analysis are extracted resistors netlist, initial node voltages, and temperature distribution. With this input, interconnectors are constructed, and numerical integration is performed of the stress equation. Voided segments are detected, and conductance change is calculated periodically, which is followed by updating voltage drops in all nodes. If a threshold voltage drop is obtained, this time is considered as a time to failure. Monte Carlo loop around these simulations is implemented for statistical analysis, which takes into account the random distributions of critical stress and diffusivity. The first step for the validation of a developed methodology involved analysis of a special grid-like test structure consisting of two metal layers, M3 and M4, with orthogonal directions. Three-terminal voltage supply scheme is realized with cathode in the center and two anodes in the corners. This connection provides a lot of redundant paths for current flow from both anodes to the cathode, and voiding of any segment with high current density results in current redistribution and voiding of another segment. Voltage drops on all wires and VS were measured and employed for the model parameters calibration. The multiple voiding in the grid causes voltage increase in all nodes. Increase of voltage drop between cathode and anodes denotes overall resistance increase of the grid, and hence it defines the grid failure. For this voltage drop evolution, good fit of simulation and experiment has been obtained. After the model calibration using the measurements for one sample, we used it for extraction of time to failure statistics. First, for the case of uniform temperature of 350 degrees Celsius. Random values of diffusivity and critical stress were prescribed using Monte Carlo simulations, and with these random distributions, we see good fit of time to failure distribution with experiment. Note that the simulated mean time for the first void nucleation is notably smaller than the grid mean time to failure, which demonstrates again importance of the redundancy. The same model was used for simulation of a grid failure in the case of non-uniform temperature distribution. In this case, in the horizontal rails, voiding probability increases in the nodes where the temperature gradient creates EM flux divergency, while in the case of constant temperature, voids appear near the cathode. In this case, they appear near the anodes. Good match of time to failure distribution with experiment proves the ability of a developed EM model to describe impact of non-uniform temperature. The second step for the methodology validation is EM assessment of a realistic on-chip power ground grid. In a dedicated test chip, the devices were substituted by quasi-cells with polyresistors, which allowed to perform accelerated tests at 350 degrees Celsius. VDD and VSS made supply voltages to the quasi-cells with polyresistors. This grid consists of layers M1 to M4, and layer M5 serves as heater, which creates vertical temperature gradient in the grid. Connectivity to VDD and VSS ports through M3 and M4 rails provides higher redundancy for voltage supply to the quasi-cells. Higher current density in M4 layer resulted in fast EM degradation in this layer, but then the redistributed current caused also voiding in layers M3 and M4. Layer M1 consists of short paths which were immortal. Calibration of model parameters allowed to obtain good fit of simulated behavior of voltage increase on VDD port with experiment. Here, the data for a set of 8 samples is demonstrated. The data spread due to EM stochasticity was described by values of standard deviations for diffusivity, activation energy, and for critical stress. From the simulations, a pair-layer voiding statistics was extracted, which demonstrated that voiding in V2 in M2 layer is mainly responsible for grid degradation. Here we see many voids under downstream V2 vias, which undercut these vias and cause significant increase of air drop. The mentioned V2 downstream vias belongs to VSS net, while in VDD net voiding occurs mainly in upstream vias. As a result, the characters of voltage evolution kinetics in VDD and VSS nets are different. Gradual voltage increase is observed in VDD nodes, and abrupt voltage changes are observed in VSS nodes. This behavior of voltage evolution is confirmed by the measurements, which again proves the capability of the developed methodology to predict the EM degradation of power ground nets. Based on the calibrated parameters, good fit of time to failure statistics and mean time to failure between measurements and simulations has been obtained. The future work should include collecting more experimental data on larger number of samples, including more representative dependency on temperature, which will allow to do more accurate calibration of diffusivity and critical stress parameters. And here are some conclusions from this work. We demonstrated that EM assessment of a power grid should include numerical analysis of stress buildup in interconnect trees and compact models for void evolution. It was demonstrated that temperature gradients are able to change voiding locations due to creation of atomic flux divergency. Time to failure of a grid is defined by EM-induced increase of voltage drop, and mean time to failure is determined by statistical distributions of critical stress and diffusivity. And finally, direct comparison of simulation results with measurements has demonstrated validity of the developed assessment methodology. Thank you.